Right, so it's a great pleasure to have Dr. Balachandra Suri today giving us a talk on his work. So Bala is an expert in nonlinear dynamics and fluids, and maybe dissimilar to a lot of researchers, he does both numerical simulations and laboratory experiments, which is a very nice combination. So as I said, he's interested in nonlinear dynamics, things like pattern formation, bifurcations, with special applications perhaps to fluid dynamics, where he likes to study coherent structures and stability and transition to turbulence. In addition to that, he also has interests in topological data analysis, things like persistent homology. So it's a very nice combination of tools and application areas. Bala did his bachelor's and master's in science from the Indian Institute of Technology in Kharagpur. He then went on to get a PhD in physics from Georgia Tech, where he also got a minor in mechanical engineering. So once again, combining sort of different ways of looking at things. So after that, he was a postdoctoral fellow, and currently he has been at the Institute of Science and Technology in Austria from 2018, where he's currently based, and he's giving the talk from Austria right now. So today, Bala is going to talk about capturing turbulent dynamics and statistics in experiments using exact coherent states. It's a mouthful, so I'm sure he'll explain all the words. So over to you, Bala.
Thanks a lot, Vishal. So as Vishal mentioned, I'm now a postdoctoral fellow at the Institute of Science and Technology, Austria. And part of what I'm going to present today is from my PhD, the later half of my PhD. And after I graduated from Georgia Tech, I was also collaborating with Roman Grigoriev, and I was doing numerical simulations with him. And this work is rather a full picture of what coherent structures are. So I chose to focus on this. So as Vishal mentioned, my research interests lie at the intersection of nonlinear dynamics and fluid dynamics. I've also recently started working on hydrodynamic quantum analogs, which is a system that tries to mimic quantum phenomena at a macroscopic scale. And I also am interested in physics education research, like teaching hands-on research to undergraduate and high school students and so on. And the ones here highlighted in bold are the topics that I am currently working on. So for today's talk, I'm going to discuss what are called exact coherent states and how we capture statistics and dynamics in experiments using these. But I'll start with a slightly broader area, which is spatially extended nonlinear systems. As the name suggests, these are spatially extended systems, such as, say, for instance, oceanic flows, patterns that you observe in biological systems, zebra, tiger stripes and fingerprints. And also dynamics, for instance, the dynamics of the brain or the dynamics of the heart and chemical reactions. These are just a few examples of a larger class of systems which are all governed by nonlinear partial differential equations. Now, what is also common across these, besides they being governed by nonlinear PDEs, is they are fairly difficult to characterize, model, and forecast. What I mean by characterize is if I give you a time series of these systems, say, for instance, in a fluid flow, I give you the flow patterns at various instants, and someone asks me what are the key features that you would extract to quantify this time series. It's a fairly challenging problem. And of course, because these are governed by nonlinear partial differential equations, technically, it's very difficult to numerically simulate these, and we want reduced order models to efficiently describe. And of course, it's very challenging to forecast these systems. We know that we cannot forecast the weather for longer than a couple of days into the future. Now, why this is, we'll shortly discuss. So the fundamental difference between linear and nonlinear systems and the challenges involved stems from how we can solve these systems. Let us think of a dynamical system. Say You have, when I say dynamical system, I'm talking of something that has the form u dot is equal to mu. Now, if the system is linear, then here u is what we call the state vector. So if you have a pattern, you can think of it an image as an image. You jot down all the pixel values into a large column vector, and that describes this pattern completely at any given instant. Now, as the pattern changes, that's the system is evolving, this vector changes. So you define an evolution rule such as this. Now, if your uh, governing equations are linear, that is, m is not a function of u, then you can simply write the solution to the differential equation as follows. And the nice thing is, you can evaluate this exponential term once for all, and any initial condition is just a product of this times the initial condition. So any evolution, I mean. So essentially solving linear equations is kind of now, like, we know how to do it. Well, we also know how to solve nonlinear equations. Just the problem is when you have a coupling term, here I'm choosing a specific form of coupling where n is nonlinearity and it's also a matrix, let's say, that depends on the state vector. Now, as the system evolves, this coupling is also going to change. And so you cannot write a simple form like this, e power mt times u naught, to solve these equations. And that is the fundamental, problem that we are trying to address. How do you solve these equations efficiently? Now, there is a lot of insights that we gain from experiments and numerical simulations, and it turns out that solutions to nonlinear equations can be steady or oscillatory, just like linear equations, but there is also a different class of solutions that are not observed in linear systems, and that's chaotic solutions. This brings us to what is chaos. So let us look at a nonlinear ordinary differential equation, just three differential equations here coupled, and the nonlinear term is xz in this equation and xy here. Now, for a suitable choice of parameters a, b, and c, if you integrate this equation using a computer, you get a time series that never repeats itself. Now, that is one property of a chaos, is that the state of the system, that is x, y, and z, do not repeat simultaneously ever exactly. There is also another important property of chaotic systems is exponential sensitivity to initial conditions. So here I'm going to show what is called a state space visualization. We'll use quite a bit of these today. So you have the state of the system x, y, z. You plot them along three axes, x, y, and z, and you visualize the evolution of a system as a trajectory. Now, if you have two initial conditions that are close by at t is equal to 0, after some time they start separating. But after a finite amount of time, what is called the Lyapunov time, the system tends to lose memory of how it started. So you cannot predict the evolution of a chaotic system for longer than a few Lyapunov times. It's a fundamental limitation. So another challenge with chaotic systems is how we retrieve statistical properties. So if I were to say, what is the standard deviation of this signal, then you have to resort to computing it numerically. So to address these, challenges in low dimensional chaos, there has been a lot of work trying to identify order in chaos in the form of so-called invariant solutions or non-chaotic solutions. So if I plot the time series of the Lorentz system x versus z, I get this plot which is called the chaotic attractor, or we typically call it the butterfly plot. Now at the center, you see two unstable equilibrium solutions, meaning if you start at these points, you stay there forever, but they are unstable in the sense it's like a position at its inverted, a pendulum at its inverted position. So you tip it a little bit, you start getting dynamics again. Now, in the hierarchy of solutions, there are also unstable periodic orbits, which are dynamically very important. So you start on a periodic orbit at any given instant, then you end up after a finite time exactly at the same location. But because these are unstable again, your dynamics do not converge onto these solutions. So the idea is then you can describe a chaotic time series as following one solution at an instant, a later solution at an instant, and so on. So you are basically dividing or decomposing your time series into chunks of non-chaotic solutions. The advantage of doing this is essentially you can then write down your statistical averages, temporal averages as a weighted summation evaluated over these non-chaotic solutions. This is something we are familiar with quantum mechanics, for instance, where you have basis functions and you can use ergodic hypothesis to retrieve temporal averages using like weighted average over your eigenfunctions. So the question is then, we know that this is feasible in low dimensional chaotic systems. Can we actually extend a similar description to spatially extended chaotic systems such as fluid flows? So here is a brief outline of the talk. So we'll go over order in chaotic flows, that is the notion of coherent structures and exact coherent states. I'll go over what quasi-two-dimensional Kolmogorov flow is, which is our experimental setup and where we do all our numerical simulations. And then we discuss two classes of non-chaotic solutions today: unstable equilibrium solutions, that's the inverted pendulum example, and then the unstable periodic orbits, which are closed loops that we have discussed. And then I'll briefly go over the topology of transiently chaotic dynamics in Kolmogorov flow. So why fluid flows? Of course, we know that they are almost everywhere in our everyday life, whether it is biological systems or, say, for instance, we open a faucet. But from a theoretical standpoint, they are also very convenient because they have well-defined governing equations in most cases. And in laboratory experiments and numerical simulations, we have access to spatiotemporally resolved data, numerics or PIV data in experiments. So for me, someone who is interested in like testing the nonlinear dynamics approach to fluids, they are very convenient in terms of fleshing out these novel techniques. So we'll confine ourselves to the flow of fluids such as water, which are Newtonian, and these are governed by the nonlinear partial differential equation, the Navier-Stokes equation, which is nothing but Newton's law for a continuum. So here is the acceleration term, and this term tells you the nonlinear term is essentially the advection of momentum. For a real fluid, you would have viscosity, and this is the viscous dissipation term. And the body force includes gravity and so on. And we are also assuming the flow is incompressible, conservation of mass or volume, essentially. Now, what is interesting is the term Reynolds number here. This is a parameter. This governs the relative strength of the inertial terms, the nonlinear terms, and the dissipation terms. For low Reynolds number, you have a smooth flow spatially and temporally, and this is called a laminar flow. Here you are seeing flow in a pipe seeded with some aluminum flakes. Now, as you increase the Reynolds number, you start finding spatially and temporally complex flows, which we call turbulence here. Now, we term turbulence high dimensional because if you look at this flow field here, you have structure at multiple scales, and also if you take a time series at a single point, you will find a broad spectrum of temporal spectrum there. Which means if you have to solve this equation numerically, you have to solve coupled differential equations that give you the velocity at each spatial location. Now, the question then is there any order in chaotic flows? Turns out that there is a lot in terms of coherent structures, which have been observed in wall-bounded shear flows as well as geophysical flows, for instance. So here are some examples both from laboratory experiments and numerical simulations. So these structures called coherent structures are easily discernible, and they also persist for a longer duration. That's the general qualitative picture. For instance, the red spot of the Jupiter that you are seeing here has persisted for several tens of thousands of years. And also you have coherent structures in geophysical flows. So when you see this numerical simulation by NASA, your eye is automatically, it focuses on these giant vortices here. So there has been a lot of efforts on describing turbulence using coherent structures, which are often empirically defined. But what we are going to do is kind of take a hybrid approach between using governing equations and trying to fit the coherent structure picture into solutions of the Navier-Stokes equation. So it's not entirely an empirical way of defining what a coherent structure is. So this brings us to the notion of exact coherent states. I'll keep drawing analogies with the Lorentz system, so that's the reason this plot is here, the time series. So these are flow fields that are exactly steady or time periodic, and these are solutions to the Navier-Stokes equation. Okay, and exact coherent structures by definition exist only in numerical simulations because they are unstable. So I'll have to make that clear at the beginning. Now the question is, why or how do we intend to model turbulence using these solutions? Well, so here I'm showing a bunch of flow snapshots. I'll tell you what these flow snapshots are in a little while, but this is a video, you can think of it. Now, if I detect a coherent behavior of the flow at a certain instant, the idea is I compute an exact solution of the Navier-Stokes equation which mimics this coherent behavior. And then at a later instant, I find another coherent behavior. So I will compute another exact coherent state that mimics the later behavior. So the flow is expected to be following one exact coherent state at a given instant, another state at a later instant, and so on. So this is the big picture that we are going to flesh out today in our talk. So there have been a lot of previous studies, mostly focusing on plane coet, pipe, and channel flows in terms of understanding or computing these invariant solutions. Now, what is common across all of these numerical simulations is they have imposed spatially periodic boundary conditions, meaning if you take a pipe, the velocity field at the entrance of the pipe is exactly the same as at the exit. Now, that is an unphysical constraint on flow because that's not what laboratory experiments are. Also, quite a few of these studies have imposed what is called the minimal flow domain, have been performed on minimal flow domains, meaning this is the smallest unit of fluid flow that can display turbulence. So the problem is, again, these cannot be realized in experiments. Consequently, there is very limited evidence for the dynamical relevance of exact coherent structures or states in experiments. Now, all the previous studies are in pipe flow, where you perform a measurement of the flow along the cross section and you have some pre-computed solutions and you see whether you observe similar patterns or not. And there was no evidence for the dynamical relevance. What dynamical relevance means, I'll get to it very shortly. So to address these shortcomings, we started studying quasi-two-dimensional flow, which is a model of geophysical flows typically, and it is generated in a shallow electrolyte layer. Here is our experimental setup. It's the size of an A4 paper, so it's a tabletop experiment. We have a rectangular container with an array of permanent magnets laid out at the bottom. The magnets are edges and magnets have opposite polarity, either out of the page or into the page. Then we pour a layer of copper sulfate solution on top of these magnets, and we pass a direct current through it. So adjacent magnets, the Lorentz force J cross B drives the fluid either to the right or to the left, and so you get a sinusoidal shear flow. Now, in experiments, we visualize this flow by seeding the flow with glass spheres and performing what is called particle image velocimetry. Sorry, this seems to be. Yeah. So what you do is you put tracer particles on your fluid surface and let the flow evolve. And then you take a video of the flow, and then you compute what is the displacement of the tracer particles across successive images. And if you do it at each spatial location, you get a spatially and temporally resolved velocity field. Now the color here is vorticity, which is the curl of the velocity. It tells you whether the fluid is rotating to the left or to the right. So for the rest of the talk, we'll be focusing on vorticity because in 2 dimensions, it is sufficient to describe the flow quantitatively. Now, turns out that there need to be some modifications to the Navier-Stokes equation to describe flows in shallow electrolyte layers. So this is the governing equation that we derived. Now, the key difference compared to Navier-Stokes is the addition of a linear friction term here, because when you have a fluid layer of finite thickness on a solid surface, you have a boundary layer that is generated. So the bottom of the fluid is at rest and the top moves at a greater speed. So there is friction stemming from this velocity gradient, and this is modeled using the term minus gamma u here. And there is also the fact that the net inertia or momentum transport of the fluid on average is smaller than what you observe at the free surface. So the nonlinear term has to be scaled with a parameter beta, which is typically less than 1, 0.75 approximately in our experiments. So we developed a second order finite difference code of this governing equation. Now the key features of our numerical simulation are that the size of the numerical simulation is identical to the experimental domain. And then we have imposed no slip boundary conditions. So these are physical boundary conditions. And we have also taken a lot of care in modeling the forcing profile in the experiment. So here is the red curve here is my model for the electromagnetic forcing, and the black dots here are the magnetic field measurements from the experiment. So we have really spent a lot of time trying to get the model, the numerical simulation to mimic the experiment as closely as possible. To give you a preview of it, so here is a laminar flow at very low Reynolds number, around Reynolds number 6 that we observe in the experiment. So you get alternating bands of fluid. It's a shear flow essentially with the sinusoidal profile. And here is our laminar flow from the numerical simulation. So we also computed the sequence of bifurcations leading to onset of chaos or turbulence in the system, and we found quantitative agreement. Yeah.
Could I ask a question?
Yes, please.
So in this thing, what's the Reynolds number?
So the Reynolds number is essentially defined as, okay, sorry, I didn't have it here. It's the RMS velocity computed at the free surface.
But how much is it numerically?
So that's, I have it in the next slide.
Okay.
So,
because I was seeing that the corner effects are very small in your experiment. So I was wondering how that is.
well, so it turns out that we do have to impose real boundary conditions. Otherwise, the dynamics actually don't even agree in the pre-turbulent regimes. So I mean, you do have these vortices at the corners which are kind of pinned, but they do play a very important dynamical role.
Okay, thanks.
In the sense, in terms of what flow patterns you observe.
Sorry, one
So
question. So can you explain once more how you drive with this magnets?
So the magnets are laid out at the bottom of the container, and then you pour an electrolyte on top of the magnet array and just pass a direct current. That's your experimental setup.
You pass in, okay, and
so then the magnetic field, the J cross B, the Lorentz force drives the flow either to the left or to the right in the fluid.
So the magnets are of alternate polarities.
Yes, yes.
Okay, fine.
And there is no time dependence in terms of forcing. It's just that the Lorentz force drives the flow. And then if you drive it sufficiently hard, you start getting time dependence in the problem. Is that
okay,
clear?
Thanks. Yeah.
So as we increase the Reynolds number to about 20 or 25, we start getting spatiotemporally chaotic dynamics. So I'm going to list out a few numbers here. So this is the vorticity plot, a video at Reynolds number approximately 24. And the temporal correlation time is about 30 seconds. This means on average, flow fields differ from themselves after every 30 seconds. And here is a plot of our kinetic energy, which shows, like it's fairly chaotic or noisy. Another metric which is more relevant in terms of a dynamical system is the Kaplan-York dimension, which is the effective dimensionality of your chaotic attractor. Just like the Lorentz attractor, when I showed you, it's approximately 2, whereas here the dimensionality is approximately 12, and you get a number from this, which is the Lyapunov time, which tells you what is the order. It's not exactly the farthest you can predict, but typically the order of time beyond which you cannot forecast the system. So it's about 1 minute in our case, and all forecasting or modeling has the limitation that it's maybe a minute or two into the future. So that's the idea. So, okay. So you have now a chaotic time series, essentially a video of snapshots or a vorticity plot. How do you extract signatures of unstable non-chaotic solutions, which we will be focusing on? So the first class of solutions we focus on are unstable equilibrium solutions. As we mentioned, this is nothing but this is similar to the pendulum at an inverted position. So you need to understand or extract dynamical signatures from your time series. So when you have a pendulum that is rotating and it reaches the inverted position, you know that it slows down. And we use this analogy and we compute the rate change of turbulent flows. So you have a flow snapshot at a given instant, and you have a flow snapshot at a next instant in your experiment. So you compute the difference and take the L2 norm over the entire flow field. The idea is if you are mimicking the behavior of an unstable equilibrium, then the evolution of your turbulent flow field should slow down. Now, when I mean slow down, it is the evolution of the flow pattern, not the movement of the flow particles in the physical space. I'll demonstrate this using this video. So your turbulent flow field is changing now, and then it has slowed down a little bit, and then it slows down even further, which corresponds to this deep minimum here. And then because this is an unstable equilibrium that it is supposed to mimic, you fall back into chaos again. I'll play this video again.
Bala, question.
Yeah, please.
So it is slowing down because it's living on the stable manifold, is it? Stable manifold of that attracting manifold of some kind of saddle point there. Why
Yes.
is it
So the
slowing
idea
down?
is it is approaching the saddle point through this along the stable manifold.
Along the stable manifold, right? But how does it go to the stable manifold? It's just because it's an attractor. You assume that everything
Yes.
is going towards the, okay.
Well, but it's a saddle, so it will not go to the stable manifold. It will fly
It will go
past the
near.
state. Yeah.
Okay.
So then what we do is we have the turbulent flow field at the instance where it has slowed down dramatically. So let us say that is this black sphere here. And then the goal is you have to compute a similar equilibrium solution from the numerics. And the way we do it is we employ a Newton-Krylov solver. We plug the experimental snapshots, that's the PIV data, directly into our numerical simulation. And we iterate till the rate change of the turbulent flow is identically zero. So in some sense, you are starting with this black sphere here on the pendulum, and then you kind of iterate over and you compute the inverted position of the pendulum. Now, instead of doing this in 2 dimensions for a pendulum, you are actually doing it in a 10 raised to 5 dimensional, you're solving a 10 raised to 5 dimensional equation. So here are some examples that we have. So the top are various snapshots from the experiment where the turbulent evolution has slowed down. And the bottom are unstable equilibrium solutions computed directly from experimental data. So these are numerical solutions at the bottom, and the top is experimental snapshots. So there is a very nice way of rationalizing why these unstable equilibrium solutions have even converged in the numerics. So this can be done by using state space visualizations. So here what I'm doing is I'm projecting. So you say your entire turbulent snapshot is encoded into a large column vector, which has the dimensions 10 raised to 5. Then you project it into 3 convenient basis functions. Now I'm not going to tell what these basis functions are, but it's a 3D visualization of a high dimensional state space. Each point on this state space represents a flow field. And the tortuous trajectory that you are seeing here is the turbulent evolution. So this is an equivalent representation of your time series in physical space. And these spheres here are the various unstable equilibrium solutions that we computed in the DNS. So what is happening is the turbulent trajectory, as it is evolving, it is going through the neighborhoods of these solutions. And when you are close to one of these solutions, like here, say for instance, you mimic the spatiotemporal properties of that solution. So the The solutions look similar in physical space because you are mimicking the spatial properties, and you are slowing down in the physical space because you are mimicking the temporal property of an equilibrium solution. So this was the first, sorry, yeah,
question.
Vishal. Yeah.
In what sense are these equilibrium solutions different from one another? In the case of the Lorentz model, there's a simple idea of the number of times I sit on one side of the butterfly or something.
So
is there a
so these are different
here?
No, these are inhabiting different regions of the state space. So they are, so say for instance, if I'm correct, in the Lorentz, the two equilibria are actually symmetry related copies. Right? It's yeah, but here there is no direct relation between these equilibrium solutions. Typically, these are born out of saddle node bifurcations, and they just exist there in the state space.
But is there some parameter that tells you which equilibrium solution you're at? I mean, there must be a continuation parameter, right?
No. These are all, so all these solutions are at the same parameter, and these are, they coexist. So there is in some sense you have multiple solutions. I mean, that's a hallmark of nonlinear equations, right? You have like multiple solutions to the governing equation.
Right. I guess
so,
I'm just trying to think in if the claim is that the solution to the problem remains close to one of these through its time history,
it only
then
no, it only remains close to one of these transiently, not forever.
Right, but I would then like to enumerate the collection to talk about a possible approximation or make a density argument that just as periodic orbits are dense. I mean, this is what I'm trying to get at, is in what way can I label or enumerate or categorize them?
So clustering, I'll get to clustering in the next section, because I did cluster equilibrium solutions, but it's a little bit tricky because you have quite a few of these which can be similar to each other, and they may be related via bifurcations. If you continue parameters, you will know that. But we haven't actually done a very thorough analysis of that. With periodic orbits, we have done to some extent.
Okay.
So
okay, thanks.
We have labeled, I mean, these are labeled, and there is some sort of sorting that I have done, but I wouldn't call that, because it ultimately boils down to how many solutions you have. If you have 100 of these, then yes, it will be really useful, like clustering them and sorting them based on, say, their eigenvalues or their physical features. But we haven't actually done that, and that's.
But your phase space is infinite dimensional.
Yes, but the idea is only a few of these are dynamically relevant.
Okay, so just a clarification here. So like apart from these equilibrium solutions, they're going to be periodic solutions of all periods, right, in this thing?
Yes.
And so the turbulent wiggle line that you're showing will only be close to some of those. It need not always be close to an equilibrium solution.
No, it can be close to a periodic orbit or an equilibrium or a 2 torus.
Right.
Yeah. So I'll get to these actually. I mean, it's there in the later half of the talk. So this was, I would say, the first evidence for these solutions being fleetingly visited experimentally and governing the governing the dynamics in experiments. So then the question is, unstable equilibrium solutions by themselves don't have any dynamics because they are steady flows. Then how do you actually understand turbulent evolution around these solutions, right? This brings us to the question, this brings us to understanding the evolution or constructing the neighborhoods of these solutions. So you start with your governing equation, and instead of, you basically do a change of origin of your Navier-Stokes equation. You can think of it like that. So if you are near a solution, then you focus on how the perturbations to this solution would grow in time. So, and then you do a Taylor series expansion in terms of the perturbations here. And the first term is 0 because the f of u naught is 0 for an equilibrium. So you can develop, you arrive at a linear equation that governs the growth of infinitesimal perturbations to this equilibrium solution. So you do it for every equilibrium. And once you have a linear equation, you can compute the eigenvectors of this matrix, which is called the Jacobian, which tells you how different perturbations to my equilibrium are growing or decaying. And finally, you can express the evolution of the turbulent trajectory as a summation of the expanding and contracting eigenmodes. So the contracting eigenmodes have real parts of their eigenvalues are negative. The expanding modes, the real parts of their eigenvalues are positive. Now, what does this mean? So in the state space picture, you have the turbulent trajectory approaching the unstable equilibrium along the stable manifold, that is the contracting eigenmodes, and it is departing from the neighborhood of the unstable equilibrium along the unstable modes. That's the repelling directions here. I hope I haven't mixed up the stable and unstable, but stable is contracting, unstable is repelling here. So now, in principle, if you compute all the stable and unstable eigenvectors around an equilibrium, once you know you are close to the equilibrium, you can forecast the evolution of the turbulent trajectory using a linear model. But you can also do a lot of dimensionality reduction if you look at the asymmetry between the number of stable and unstable directions. So typically what happens is these solutions that are dynamically relevant have only a few unstable directions, typically 10 or 20. So the stable manifold dimension then is very high, so of the order 10 raised to 5. So what you can do is you say, I will not concern myself with the approach to the equilibrium, but I'll only concern myself with how turbulent trajectories depart from the neighborhood of the equilibrium. So you ignore the contribution from the stable manifolds and just focus on how turbulent trajectory is departing from the neighborhood of the equilibrium. And we hypothesize that it should shadow the unstable manifold of the equilibrium. Right? So this has been shown numerically by Gibson and Predrag Cvitanovich in numerical simulations of plane coed flow. But experimental evidence for this was fairly scarce. So what we did was we looked at our experimental time series and identified an equilibrium that we computed from it, which has 7 unstable eigendirections. So the unstable manifold is 7-dimensional. So this is the equilibrium here, the middle snapshot here. But what we realized is that the leading eigenvalue is 10 times larger than the rest, meaning because there is an exponential growth, any turbulent trajectory that approaches this solution should depart following this one-dimensional unstable manifold. And here is the mode, unstable mode corresponding to that equilibrium. And so you would expect the turbulent flow in the physical space to start having some dynamics in this region in the physical space. So here is an example. So here you are seeing the experiment evolving, and this is the 1D unstable manifold that has been constructed using the equilibrium. And this is another example from the simulation where the turbulent flow just shadows the unstable manifold. Now, what we realized is that even though we started out with a linear model of the dynamics around the equilibrium, you can also compute the nonlinear extension of the unstable manifold by basically plugging in an initial condition of this form into the numerics. And what we observe is that this curved region here, the curved region here is actually the nonlinear extension of the unstable manifold, and the turbulent trajectory shadows even the nonlinear extension. So it's a fairly large region of state space actually. Around 2 Lyapunov times we are able to forecast turbulence using an equilibrium solution. Okay. So
sorry, I had some questions. Yeah, so so in the experiment, the way you identified the equilibrium point is by looking at this S of t, is it?
Yes.
So you look at the minimum of that.
Yes, so if you look at the video starts very slowly because you are near an equilibrium, so you evolve very slowly, and then as you move farther away from the equilibrium, you start getting dynamics. So here you are near the equilibrium. Yeah.
So what are the three points?
So where here in the state space projection here? So these are the projections of the turbulent flow onto the eigenmodes of the equilibrium. So the first mode is E1, E2 and E3 are other modes, but you see that the dynamics kind of grow along E1 very rapidly because of exponential growth. So if you are in the linear regime, then you should have a straight line, and that is what you observe here in the experiment as well as in the numerics.
Okay.
Okay,
but I had just one more basic question. This so if in the initial part, how did you actually compute this function S of t?
So we take the difference between successive flow snapshots and compute the L2 norm of the difference. So if a turbulent flow field is changing, then the difference between successive snapshots should be quantifying that change.
Okay, so it's basically like the Lyapunov exponent in some sense.
Well, not exactly, because we are not perturbing the turbulent flow field, right? For the Lyapunov exponent, you compute what is the growth of the perturbation.
Right.
Whereas here, you are just computing what is the difference between flow fields. It's like a velocity. You are computing the velocity of in the state space or the speed in the state space.
Okay.
So if I'm looking at this picture, it tells me how fast this curve is being traced in the state space. S is actually what we term the state space speed. So,
sorry, may I ask a quick question?
Yes, please.
No, I mean, to get back to Abhishek's question, I mean, this is one of the ways you do compute Lyapunov spectra in some complicated nonlinear dynamical system, right? I mean, it might be much higher.
Well, to compute Lyapunov,
the whole spectrum.
I'm not.
I mean, you take the linearized map and you follow the linearized map, or you're only doing it at one point.
Yes, exactly. Yes, but yes, exactly. The way we compute these eigenvectors is similar to how you compute a Lyapunov spectrum. I'm not contradicting that. It's just that once you compute the eigenvectors, then you are essentially using the governing equations to evolve along these eigenvectors.
Along the linearized thing, yes. That part you don't.
Along the linearized as well as the nonlinear, because we don't,
of course,
because the linear,
right.
Yeah.
So here you just do one shot or what?
Yes, so we do it only for one equilibrium at a time, because when you are close to an equilibrium, you only require the linear model corresponding to that equilibrium. So at a later point, if you are near another equilibrium, you compute the linear model around that equilibrium. So you're basically patching your turbulent evolution whenever you are close to an equilibrium by using the corresponding linear model.
Okay.
And of course, then, sorry,
continue. I'll ask a bit as soon as you're done.
Yeah. So then in the hierarchy
I have one question.
No
the actual eigenvalue that you mentioned, the largest eigenvalue, what's the actual value in this case?
So in non-dimensional
because you
units,
mentioned
0.1.
you were able to predict this up to, I forget, you said 5 times or 10 times the Lyapunov time scale.
Two Lyapunov time scale,
something, yeah. But that basically just depends on the eigenvalue, the leading eigenvalue, right? Essentially.
Not exactly. So the Lyapunov time is
the
a
larger
global measure of
eigenvalue,
chaotic system.
Right. Yeah, exactly. So, but that's partly irrelevant in this case, essentially, because if you're so close to the equilibrium, the unstable eigenvalues of the equilibrium matter more than the global Lyapunov time scale.
Yes. But
so that's why I was asking, what is the time scale? What's the eigenvalue in this case?
So in dimensional
compared to
units,
0.02, which you had, so the largest Lyapunov exponent was 0.02, I guess. And
yes, and here it is 0.14. So the Lyapunov exponent is 0.14. So if I divide it, then it would be of the order of around, I would say, 5 seconds maybe.
Yeah. Okay.
Yeah. There is the subtlety. I'll get to the end, because actually the leading eigenvalue of an unstable manifold does not repel from the unstable manifold. I'll just get to that subtlety later, because unstable manifolds are attracting in nature. So they actually tend to attract the dynamics rather than repel. So this plot actually shows you that the unstable manifold is attracting the dynamics via the stable manifold. So I'll get to that later, but that's okay. That's a subtlety which is not really particularly relevant.
Question.
So
yeah, how you explained something about why there are 10 to the 5 stable directions and only 7 or 8 unstable directions. Can you repeat why you said that's the case?
So one of the reasons is that the dynamics are confined to an inertial manifold of a much lower dimensionality, which means that the unstable and stable, the dynamically relevant stable directions are also of the order 10 actually.
Okay.
But it's just that the complete stable manifold in the full space is 10 raised to 5.
So why is the complete stable manifold so much more than the unstable?
Because
again,
the stable plus unstable.
Ask the same question.
Yeah, no, because the stable plus unstable manifolds.
Very close. Sorry, continue. Excuse me.
Sorry, because the stable plus unstable manifold dimensions should be the dimension of the state space, right?
Yeah.
So that is 10 raised to 5.
Yeah.
And if I have to compute what is the effective dimensionality, then I would probably go with the number, say, of the order, say 20. And then you have 10 unstable directions and probably 10 stable directions. That is the dynamically relevant one. So
no, but is it because your flow is not very turbulent? It goes back to Rama's earlier question of what is the Reynolds number. I mean, is this sort of analysis good only near onset, or it's good for statistically homogeneous isotropic turbulence?
there is some evidence that this can be extended as high as, 3D pipe flows. These solutions have been computed as high as like Reynolds number 5,000 and 6,000.
No, but what's the transition Reynolds in that case?
Well, there is no transition per se in those, because the base flow is linearly stable. I
know, but you know what I mean. You know, the Bjornhof, you're in that group.
Say, let us say 2000. Yeah, so 2040 is the number that we typically quote in terms of transition to turbulence. So anything over 2300 or 2400 is fairly turbulent.
I see. And they're also, okay, fine, continue. Sorry for getting so technical.
No problem. So yeah, actually there is a study that computed signatures of these solutions at Reynolds number 35,000 in pipe flow. So there is some hope that we can push this to much higher Reynolds numbers. It's just that it is computationally fairly challenging at this point, but there is enough hope. So now, in the hierarchy of solutions, unstable equilibrium are the most elementary ones. So the next are unstable periodic orbits. These are solutions that repeat exactly after a finite amount of time, but again they are unstable, so you don't exactly land on one of these solutions. The way we detect these solutions is using recurrence analysis. So if you have a turbulent snapshot at a given instant, you compute the difference with the turbulent snapshot at a later instant. So if the snapshots have, if the snapshot has repeated or a similar snapshot has appeared, then you should observe a minimum in the recurrence plot. So here is the recurrence plot where T tells you the time along the turbulent evolution, and tau gives you some sort of a delay parameter. And when you have a periodic like signal, you get these bands here. So then once again, what we do is we start with an initial condition that satisfies u of t is approximately equal to u of t plus the period. And then we use a Newton-Treilhau solver and we compute the unstable periodic orbit here. So we have computed 7 unstable periodic orbits. I'll just show an instance from the numerical okay, I'll skip that probably. But so once we have computed these numerical unstable periodic orbits, we set out to see whether the experimental turbulent trajectory shadows or approaches these solutions. So what we do is we have the turbulent time series. We compute the distance from the turbulent time series to any point on the periodic orbit, and we plot it as a function of time. And then what we do to say that they are evolving at the same rate is we correlate time along the periodic orbit with the time along the turbulent trajectory. And when we do this, we get this combined plot where you are seeing that the turbulent flow in the experiment is approaching an unstable periodic orbit because the distance goes to minimum. And then the time or the correlation between the two has this one-to-one correspondence, which means if you look at in combined phase and physical space, you see that the turbulent flow is evolving in the experiment and it comes close to the periodic orbit, then starts shadowing the periodic orbit. And if you look at the flow features in the physical space, they look fairly similar as well. And then after a finite amount of time, you leave the neighborhood of the unstable periodic orbit. Here is another example from the experiment. So you are shadowing the unstable periodic orbit at a comparable rate, not identical. And then because the periodic orbit is repelling, you move away. So now this brings us to the question. So when we started our analysis, we wanted to say that we could decompose our turbulent trajectory into smaller chunks and approximate each chunk using an unstable periodic orbit or an equilibrium or so on. Now that would be feasible if your turbulent trajectory is spending a sizable fraction of time in the vicinity of these solutions. So what we did is we computed the survival probability, that is the fraction of the time the turbulent trajectory spends near the epsilon neighborhood of a periodic orbit. And what we found is that if we choose a reasonable threshold of 0.45, the turbulent trajectories in the DNS as well as in the experiment spend about 30% of the time near the set of 7 periodic orbits. Now, this is only a lower limit because we only identified 7 periodic orbits, and if we identify more, this number is only going to go higher. Then what we did is we also wanted to identify which of the periodic orbits are statistically significant, meaning turbulent trajectories spend a larger time in their neighborhoods. Now for that, what we do is we have to cluster the solutions, because if you have two periodic orbits that are fairly similar, say they are born out of a saddle node bifurcation, then your turbulent trajectory doesn't see the difference between these two periodic orbits. So we clustered our 7 periodic orbits into 3 clusters, and we found that you can actually distinguish the statistical significance of these periodic orbits quite clearly. So there are 2 clusters that are quite frequently visited in the DNS and experiments, and then these solutions, a pair of these are not statistically significant. Now, why is computing the statistical significance important? Because the ultimate goal of this approach is, if we find enough of these periodic orbits, we should be able to retrieve turbulent statistics as a weighted summation evaluated over the periodic orbits. Now, one could interpret that the weight associated with each periodic orbit in the summation is related to the fraction of the time turbulent flows spend in the vicinity of the periodic orbit. Which means if your turbulent flow is spending a sizable fraction near a periodic orbit, then you would expect the turbulent mean, that is the temporal mean, to be closer to the average computed using that single periodic orbit. And this was actually demonstrated also in numerics by Kawahara back in early 2000s. So to test that in experiment, what we did is we computed the rate of energy input and dissipation, and we plot the probability density function. And we also compute the corresponding quantities for the unstable periodic orbits that we have, and we plot it simultaneously here. And you see that the statistically significant or the frequently visited periodic orbits indeed capture the average turbulent dissipation rate to within a few percent, actually to within 5%. Whereas those which are not statistically significant are only infrequently visited. They lie near the tails of your PDF. So that's our big message, in the sense that you can not only model dynamics, but also get fairly good information about statistical properties of chaotic flows using unstable periodic orbits. I'll skip this. There is also a way to get these statistical weights using periodic orbit theory, but for lack of time, I'll not go over this. Now, I'll conclude the talk with a few videos of connections between these exact coherent states. So the idea is the turbulent flow shadows one exact coherent state at a given instant and another state at a later instant. So there is something that is transporting the flow in the state space from the neighborhood of one solution to the other. And this happens via the intersection of stable and unstable manifolds, and these are called heteroclinic and homoclinic connections. So if you have an equilibrium and you construct the unstable manifold of that equilibrium, the unstable manifold can intersect the stable manifold of another equilibrium. So I'll not go through the mathematical details of how we computed this, but here are several examples of those. So here I'm starting from an equilibrium. I choose a specific combination of unstable eigendirections. And so you are looking at the nonlinear evolution of the unstable manifold, not just the linear neighborhood. Then this unstable manifold goes and intersects the linear, the stable manifold of another periodic orbit. So you converge onto the periodic orbit now, and you perturb the periodic orbit, and you go to another equilibrium. So what we are looking at is, you are looking at network of dynamical connections that can potentially take turbulent flow from neighborhoods of one ECS to another. Here is another example. So you start from a periodic orbit, you perturb the periodic orbit, and you fly past an equilibrium solution, and then you approach a 2 torus. So you can see the turbulent flow actually mimicking a 2 torus here. And then from the 2 torus, you again go to another periodic orbit. So this is a heteroclinic connection between two periodic orbits. Actually, it's a composition. It's a periodic orbit to a torus, and then a torus to a periodic orbit. And I'll conclude with one last video. And you also have homoclinic connections. You start with a periodic orbit, and you perturb the periodic orbit in a specific way, and you get turbulent-like evolution for a significantly long duration. But what happens is the flow eventually loops back and converges back onto the periodic orbit. So this is an intersection of the unstable manifold of the periodic orbit with its own stable manifold. Okay, so what we could do is we computed a dense network of dynamical connections between these flows, and all these flows are unstable in the sense that you will not observe the turbulent trajectories converging to these flows in the experiment or in the DNS if you start from arbitrary initial conditions. And this has the potential of, trying to design control protocols in terms of, if you want to, say for instance, decrease the dissipation rate of your turbulent flow, and if there is a dynamical connection between one of these periodic orbits to the ones with lower dissipation rate, you just have to identify a control protocol or a perturbation. Now the interesting part is you don't have to have a large perturbation. If you just perturb it infinitesimally enough such that you shadow a heteroclinic connection, then you are good enough to go from one region of state space to another region of state space. So this has, and also associated with each of these solutions, you can compute a probability, and then you can start developing Markov models. There is some evidence of that, both in terms of coherent structures. This was done by Tobias Schneider back in 2007, and more recently by Burak Budunur in periodic orbits in a Kolmogorov flow. So it's quite a, a fundamental description of both turbulent statistics and dynamics in sort of a unified framework. So I'll conclude the talk here with a summary slide. So what we have shown is coherent structures are dynamically relevant in turbulence, meaning your time series actually shows certain signatures for slowing down or time periodic like behavior. And you can use a class of coherent structures, that is exact coherent states, which are direct exact solutions of the Navier-Stokes equation in capturing turbulent dynamics and statistics in experiments particularly. And we have also shown that a network of these solutions can be computed using, sophisticated tools, which I have not explained here or gotten into any detail, but it is feasible to describe turbulent evolution as a static map bouncing between the neighborhoods of various solutions. So I've gone over an hour, I believe. So I'll skip this part of the talk and probably take questions if so I also work on hydrodynamic quantum analogs in terms of understanding chaotic scattering in these systems, but I'll probably skip that for today.
Okay, thanks, Bala, for that talk. We had a lot of questions during the talk, but I'll still open it up to the audience. If you have any question, please just unmute your microphone and ask the question.
Yeah, so maybe I'll ask a question. So this, so normally in chaotic systems, like you have this route to chaos, right? Like you have these fixed points, periodic, period doubling, and so on. So here, what happens in this system?
So we haven't been able to clearly nail it down because I think it was just a matter of priorities, but what I think is some sort of either a period doubling cascade or maybe a crisis bifurcation is what I think is happening. We haven't actually, because it happens over a narrow window of Reynolds number 1, and we haven't nailed it down.
Okay.
So we know that the laminar flow undergoes a pitchfork bifurcation, and the pitchfork bifurcation leads to a periodic, the pitchfork, the secondary branch, it undergoes a half bifurcation leading to a periodic orbit. So till that point, we have nailed it down. And within a narrow window of 1 Reynolds number, the half bifurcation periodic orbit turns chaotic. So what we think is it is most likely a boundary crisis sort of thing happening there, because some of these solutions that we have computed in the turbulent regime do continue into lower Reynolds numbers. So it is quite likely that there is some sort of a boundary crisis is there. So that's what we think, but I don't know clearly what it is.
Okay, and one related sort of quick question is, so the pictures that you showed, they of this, of these patterns, typically they look very nice and periodic, and it's not like the usual turbulent thing that you imagine. So is it because you're just showing the what you call the equilibrium points, or it's because even the movies you showed, it doesn't look like the usual turbulent?
So one thing is we are only looking at the transitional regime of turbulence here, in the sense it's weak turbulence. And that's the reason you don't see a lot of activity. The other reason is because I'm not subtracting the mean flow. So if I subtract the mean flow, you would actually see that there is a lot of activity going on, but that would be very hard for the eye to kind of detect what is happening, because your eye is kind of picking some sort of a periodicity in the X and Y directions, which is the characteristic length scale between the vortices. So that's essentially what I would say in terms of, yes, the flow is not, like highly turbulent. It is moderately turbulent as what we would term it. But the spatial extent of the system is large. So from a dynamical systems perspective, it is fairly challenging that you are even seeing signatures of these solutions.
Okay, thanks.
I have 2 questions.
Yeah.
So you introduced this factor beta into the nonlinear terminal simulations, right? 0.75 or something.
Yes.
Now that was like basically hand wavily put there, right?
Not exactly. So not exactly. So we derived this equation starting from 3D Navier-Stokes equation, and we assume that there is a vertical profile, and you can decompose the velocity field as a product of a vertical profile and the horizontal velocity. This is called the quasi-two-dimensional approximation. And then you do a mean, like depth averaging, and what you are seeing is a mean flow equation. You can think of it. It's just that a certain normalization gives you beta is equal to 0.75.
Okay, I get it. Yeah, I was wondering why you get such good comparisons with the experiment. But yeah, now it's clear. The other one is like, the term exact coherent states. I mean, I've heard it in many things, but I'm not too clear what exactly you guys refer to as exact coherent state. Is it just the equilibrium states or equilibrium periodic everything or what?
So there is a, okay, I think the original idea was it with reference to traveling wave solutions in channel flow. That was the historical origin, because these streaks and that you find in near wall regions, high speed and low speed streaks, there was some evidence that traveling wave solutions actually mimic those, and that is the reason, because traveling wave solutions are exact solutions of the Navier-Stokes, the name kind of originated there. I don't think it's particularly meaningful or anything. I mean, it's an exact solution of the Navier-Stokes equation that displays features of coherent structures. That's what. So anything could be an ECS, like a 2 torus could be an ECS, or say, for instance, a periodic orbit could be an ECS. So now we have started calling these non-chaotic solutions as opposed to ECS, because that's, I think, a more fair name in terms of what we are doing, because we are not concerning ourselves a lot with physical features of the flow.
Okay, thanks.
So I wanted to just clarify one thing regarding the Lyapunov exponent of the unstable manifold of the equilibrium here. So actually, if you have an equilibrium with a large Lyapunov exponent, in the sense eigenvalue in locally, that only tells you that you would be repelled away from the equilibrium strongly. That doesn't tell you whether you will be attracted towards the unstable manifold of that equilibrium or not, because that is guided by the stable manifold of the equilibrium. So even if you have a large repelling eigendirection, equilibria can be approached closely. So that is not related to the Lyapunov exponent of the state space in any way.
Yeah. Okay. So I think I had asked that question related to this, but no, I was basically trying to understand your comment about, at least what I understood. Correct me if that was a wrong interpretation. That using the simulations, you could actually predict, basically using the simulation where the initial condition is basically a small perturbation along that along that one-dimensional unstable manifold.
Yes.
You could make a prediction that remained close to the actual solution. Is what I understood.
Well,
you
you
said,
could make a predict.
But maybe not.
Yes. So essentially, okay.
So if that's the case, then that is going to happen if the solution is going to remain near the unstable manifold, near the unstable subspace, the linear unstable subspace, for amount of time that is that's not dictated by the stable manifold, stable directions. How long it's going to stay near the
So if we are taking the 1D unstable manifold, yes. So if we are taking the 1D unstable manifold, then whether that unstable manifold will be shadowed depends on all the other 6 unstable directions, because they will repel away from this 1D unstable manifold.
Yes. Yeah.
So if you have 3 coordinate axes and 2 of those coordinate axes are repelling as shown here, you will eventually start having the repulsion, but by that time you will have traversed quite a bit along the 1D, because it's 10 times stronger.
Yes. Yeah.
And that's what we are seeing here.
Okay. Fine. Yeah.
Okay, if there are no further questions, we'll bring this session to a close. Thanks, Bala, again for a wonderful talk.
Yeah, thanks, Vishal.
Thanks, everyone, for attending. All right.
Yeah.
Bye, everyone.
Yeah.
Bye.
Thank you.